Okay, so back to our station distribution. And for doing earthquake focal mechanisms, we have some of the same issues with the network coverage as we do for earthquake locations. One, again, is that we have this very one-sided station coverage for along and offshore, and this gives us very one-sided station coverage, for instance, along the Hosgre and shoreline faults. And again, we have this sort of the sparser station coverage outside of the Parkfield and San Luis Obispo areas. And I found that the station coverage south of Oceano is really too sparse, in my opinion, to get any reasonable focal mechanisms, even reasonable composite focal mechanisms. So I'm mostly just going to be showing you things north of Oceano because I have nothing much to show you south of Oceano because of the station coverage. So I'm going to be computing focal mechanisms using my own method called HASH, stands for Hardebeck and Shearer. So our idea here was that we didn't want to just find one mechanism that fit a particular set of polarity data, assuming a particular ray path, because the ray path is very important in the earthquake first person focal mechanism because that takeoff angle determines where a particular up or down polarity is plotted on the stereogram. So what we wanted to do is we wanted to look at how sensitive mechanisms are to changing that takeoff angle to within sort of a reasonable range of takeoff angles, changing the earthquake depth for within sort of a reasonable range of earthquake depths. So what we do is this, you don't have to follow all of this on this flow chart, but basically we just come up with one set of takeoff angles. What's the set of all of the reasonable focal mechanisms that could fit that set of takeoff angles? Let's just iterate through other possible takeoff angles, come up with more sets of focal mechanisms that fit, combine all of these together, and then we have this kind of this compilation of all of the acceptable focal mechanisms for this earthquake. And if we kind of just throw out some of the outliers and kind of come up with the average mechanism, that's our preferred solution. And then we can also use the distribution of these range of acceptable mechanisms as sort of a measure of how uncertain this focal mechanism is. So if there's a 25-degree range of mechanisms here, we can say that the uncertainty of that is 25 degrees. So one of the things that this method tends to do is it tends to throw out a lot more mechanisms than a more standard method like FPFIT would do, but it really just leaves us with the mechanisms that are well constrained and are actually stable with respect to the assumptions that we used when we did the ray tracing to figure out the takeoff angles. So, so this is a set of focal mechanisms for our region here, and you can notice that compared to the size of the earthquake catalog, this is a fairly small number of mechanisms. And I've color-coded the mechanisms by their uncertainty, by their quality rating and their uncertainty. And you can see that once we get to this sort of a longshore area along the Hosgre Fault, that almost all of these mechanisms are C and D. And these are mechanisms where the uncertainty is 35 to 45, or for the blue ones, greater than 45 degrees. And that's obviously a pretty high uncertainty when we're talking about the possibility of using earthquake focal mechanisms to say something about fault orientations, because if this doesn't resolve a fault orientation any better than plus or minus 45 degrees, that's not really going to help you with fault orientation or even necessarily style of faulting. So while there are some decent focal mechanisms onshore, they're mostly in the area of the San Simeon earthquake and aftershocks and the Ragged Point earthquake and aftershocks. So for most of this region, we can't really use these single event focal mechanisms to say very much. So that's why I've resorted to composite mechanisms. For these composite mechanisms, I've drawn a box here of where there's a number of earthquakes kind of grouped together or appear to occur along some sort of linear feature together. And I've taken all the polarities for all of those earthquakes and put them together to make a composite mechanism. And these mechanisms are much better constrained than those mechanisms I showed before, that these are almost all A and B quality mechanisms. And we can compare these mechanisms with those linear features that we saw in the seismicity, and we can see for the most part there's a very good agreement between these composite mechanisms and the planar features in the seismicity. That is, we see, for instance, these dipping, dipping features in the seismicity in these regions where we see thrust mechanisms. We see all along the Hosgri fault zone, in the San Simeon fault zone, and even for these weird things in Estero Bay, we see right lateral mechanisms agreeing with the plane delineated by the seismicity. As we go inland, we see, for instance, thrust faults and thrust mechanisms for the Los Osos fault. Even though we don't have planar seismicity to compare that with, we get what we think is a reasonable mechanism, assuming that the Los Osos fault is a thrust fault. So one of the issues here, though, is to really compare focal mechanisms to these to the planar features that we see in seismicity. What I've done here is actually fairly subjective. That I've just sort of drawn a box around some seismicity and said, okay, all of that seismicity should go into a focal mechanism that I should compare to some planar structure. And so I've been working on using some techniques that more objectively assign earthquakes to planar structures and seismicity. And this is a method that's appeared in the literature that basically what it comes down to is finding the simplest fault structure that fits all of the seismicity within the earthquake location uncertainty, and it adds planes until it can fit all of the earthquakes to within their uncertainty. So this is just an example where they have some synthetic seismicity and they put one plane through it. No, that doesn't fit everything. 2 planes. No, that doesn't fit everything. 3 planes. Aha, that fits everything. And now you can assign an individual earthquake to an individual plane, and now we can more meaningfully group earthquakes together, or group together all the earthquakes that fall along a particular plane, and then compare the composite focal mechanisms for those earthquakes with the orientation of that plane. So the great thing about this that I really like is that it's completely objective. It doesn't have any parameters that I could tune to try to enforce my view of the world on this. It just does its thing. The downside of it is it can find sort of spurious horizontal planes that if there's a lot of seismicity that's floating around that's not really well fit by a fault, it tends to just draw a fault plane through at the average location depth. But that's something that the authors of this paper were aware of and that we can look out for. So I applied this back to this region of the shoreline fault and the Hosgri fault. And so this is with 2 different takes on earthquake relocation, one using hypo-DD and one using tomo-DD. They come up with fairly similar structures that correspond to the shoreline fault, somewhat similar structures that correlate to the Hosgri fault, and then this is sort of the attempt to draw that in a 3D, that there would be sort of a vertical fault plane representing the shoreline fault, and the Hosgri fault would be very steeply dipping eastward. And then there's a gray plane in here, which is a sort of a plane that's doesn't take up very many earthquakes, and also isn't very stable. That it, maybe in this case it's horizontal, so maybe it's one of these horizontal spurious planes. In this case, maybe it's another strand of the Hosgri fault. But in any case, for the purposes of just mapping earthquakes to planar seismicity features, just for this purpose of comparing that to composite focal mechanisms, I'm not really going to worry about this third gray plane. I'm just going to look at the earthquakes that map to the shoreline plane and the earthquakes that map to the Hosgri plane. So here's actually looking at the first motion polarities for some of these composite events. So in the upper left here is the composite for all of the events that were assigned by that OADC routine to the Hosgri fault. The mechanism the composite mechanism is shown as the dark line here, and the dashed line is that apparent orientation of the Hosgri fault. And you can see that this mechanism agrees almost perfectly with the orientation with that kind of planar orientation of the seismicity, except for the dip is slightly the other way, and there's no polarities in this little wedge here, so you actually can't determine the dip, I think, plus or minus 20 degrees on either side of vertical with this data, but otherwise it's in perfect agreement. This is the south shoreline, so this is everything that was assigned to that shoreline plane south of this red line here, so not to throw in this complex area at the apparent intersection of the two faults. The mechanism is shown in black, and in gray is the orientation, just the orientation of the planar seismicity and what that would look like as a focal mechanism if it was pure right lateral strike slip, and those are, again, almost in perfect agreement. So then we just have kind of the earthquakes that were assigned to the northern part of the shoreline fault here, and those earthquakes give a composite mechanism that's the black mechanism here, that's sort of halfway between what we would expect if these earthquakes were on the shoreline fault versus if they were in the Hosgri fault. So just to step back and look at individual events here, I can't actually make any high-quality individual earthquake focal mechanisms, but I can take all of the individual events with at least 8 polarities and say which of these two orientations, which of these two fault plane orientations do these polarities agree with more. And so I can just plot them on the scale here. From the red, earthquakes agree more with the shoreline fault, and the blue, earthquakes agree more with the Hosgri fault. And again, we nicely see that all the events along the Hosgri fault agree much more with the Hosgri fault orientation. Almost all of the events along the shoreline fault agree more with the shoreline fault orientation, except if we look in this cross-section here, there's some deep events apparently on the shoreline fault that agree more with the Hosgri fault orientation. So we might envision that as a sort of a slightly warped Hosgri fault or something. I won't get into interpretations of that, but just to say that other than to say that all of the events, almost all of the events above about 8 kilometers depth agree more with the shoreline orientation. And if we do that as a composite focal mechanism here, this is a composite focal mechanism for everything on the northern part of the shoreline fault running all the way up to its intersection with the Hosgri fault, just for events that are shallower than 8 kilometers depth. And, and again, you see really good agreement with this composite focal mechanism for all those events with the orientation of the shoreline fault and the pure right lateral strike slip mechanism. It's just these sort of weird outliers below 8 kilometers depth come up with a focal mechanism that's much more north-south oriented than even the Hosgri fault. But just looking at that, we can see that even though there's only this difference in strike of about 30 degrees between the Hosgri and the shoreline fault, when we do a careful job of picking out which events are on the shoreline, which events are on the Hosgri, and do these composite mechanisms, we can actually see this 30-degree difference in strike in the composite mechanisms. So we can see that these composite mechanisms agree quite closely with the planar seismicity that we saw in the earthquake locations, which is really good for internal consistency, and also gives me more confidence in saying that yes, these really do look like these are pure strike slip mechanisms on these faults. So just to go back to this figure then, just to kind of summarize what we do see in all of these composite mechanisms, we see strike slip along the Hosgri fault, along the shoreline fault, in Estero Bay, onto kind of the Point Bouchon area, and some of these offshore events. Offshore events, if we do composites, sometimes over these fairly large areas, we end up with on average strike slip composite mechanisms. We also see composite strike slip mechanism here along the Rinconada fault, along the West Huasna fault, and we see thrust mechanisms sort of an area bounded by these two sets of strike slip along the Los Osos fault, in the San Simeon earthquake area, and in the Ragged Point earthquake area. So kind of to summarize this section, due to the station coverage limitations, the really well-constrained single event focal mechanisms are pretty much limited to onshore regions and almost entirely limited to that San Simeon aftershock sequence. Composite focal mechanisms are possible north of Oceano and south of Oceano. The station coverage is so bad I can't even produce stable composite mechanisms. The composite mechanisms are in very good agreement with the orientation of known faults and the planar structures eliminated by the earthquake locations. And while the single event mechanisms are poorly constrained along the Hosgri and shoreline faults, the single event first motion polarities tend to agree with the respective fault orientations of the fault that each of those events appears to occur on. strike slip mechanisms dominate along sort of two elongated northwest-southeast trending zones. One is sort of this along-shore zone, the Hosgri Fault, San Simeon Fault, Shoreline Fault, Estero Bay, Point Bouchon area, and then a little bit further to the east, the Rinconada Fault and the West Huasna Fault. And reverse mechanisms appear to dominate between these two trends, that is along the Los Osos Fault, where the San Simeon earthquake occurred and where the Ragged Point earthquake occurred. So that's that for focal mechanisms.
Okay, questions for Jeanne on focal mechanisms or?
The southern end of the shoreline fault, your focal mechanisms look like they match the Hosgri rather than the shoreline.
Yeah, there's a cluster at the very south end of the shoreline fault and also at the southern end of that Hosgri seismicity segment where they don't actually match the fault area and they match the other fault. Those are also the worst located events of both sets. So I wonder if there's a little bit of poor locations trading into poor takeoff angles, trading into.
But one of those events was your biggest event. Shouldn't that be the largest? Shouldn't that be?
Actually, very strangely, so there was this magnitude 3.5 event in 2000. I forget the exact date, and that's one of the events on the southernmost end of the shoreline fault. And that's actually an event that we've had a lot of trouble relocating, and. I've been working with Cliff Thurber and a few other people on trying to relocate those events. Cliff thinks that there might actually be some problems with the phase data for that event, but we haven't quite sorted it out. But there's sort of something wrong with that magnitude 3.5 and its location. So it's actually, even though you would think that the biggest event would be the best located event, there seems to be something funny going on with that earthquake.
I have a question going back to when you talked about the velocity model in your first presentation and you showed some, you're really thinking through the velocity model. You started with, for the 3D, you have Thurber's velocity model, 3D velocity model?
So that's a velocity model actually I made using Thurber's code.
Okay.
Yeah.
And are there, where I'm headed is, in terms of uncertainty in the velocity model itself, are there improvements or an iteration that you're going back? How uncertain are your final results based on the velocity model? I know you talked about that, but how coarse is the velocity model? How is there room for improvement as we advance our science in all areas? Is the velocity model a big uncertain issue?
Yeah, I think there's a lot of room for improvement in the velocity model, and that's actually something we've targeted as the big thing to do in our next round of earthquake locations. And that's one of the things I'm working with Cliff Thurber on, is that we're going to attempt to do sort of a better TOMO-GD model for that whole area, incorporate more active source data, quarry blasts. We're doing more kind of human eye quality control on all of the data that's going in.
Is there, just sorry to interrupt, is
Okay.
there any work with Jackin's group to incorporate geologic lithology and rock structure into the velocity model?
Yeah, that's actually a fairly difficult thing to do, to take these models that have some very sharp boundaries between lithological units, which of course if you ray trace through that you end up with all sorts of weird reflected and refracted waves along a boundary, whereas the way it works best
Right.
for tomographies have kind of a smoother model. So we're really, I think we feel like we're going at it from sort of a different angle than Jackin's, and in the end the best thing to do would be kind of just compare our model with his model. In terms of velocity model, I feel like the velocity model is
You're comfortable
almost,
with your up to 1 kilometer uncertainty in location based on the velocity?
That 1 kilometer is my lower bound on uncertainty. And I think I figured out the amount of, I think I figured out sort of an order of magnitude of the amount of error in that velocity model. just from doing those checkerboard tests, and I've done a number of checkerboard tests and followed the results. And so that velocity model is, I would say, halfway decently constrained onshore north of Oceania. So just that kind of northeastern quadrant of that model is halfway decently constrained. Offshore isn't constrained at all. And one of the things we're actually working on is trying to fold the gravity data into the velocity model inversion, so we just have something offshore. But even with that, that's going to be that's always going to be poorly constrained offshore. And the southern part of the model, just because of the sparse station coverage, is kind of poorly constrained. And I tried to include all of that in this synthetic attempt to come up with those lower bounds on the uncertainty. But yeah, I think you're absolutely right to look at the velocity model as a source of error that's actually something that we can actually target and try to improve over the next few years, instead of just having to put in more stations and wait 10 years until we have more data.
And then I have one last question. I'll let somebody else. If there's one area that really looks like an active fold and thrust belt in this whole region, it's off of Ragged Point, it's off of the San Simeon area in the offshore, and right in the middle of that, you have your composite mechanism is pure strike slip. Have you thought of what are your thoughts on that?
That mechanism actually looks halfway decently constrained, but of course it's completely one-sided station coverage. And the other problem is, because the seismicity off there is fairly diffuse, I've taken seismicity over a really broad area. So it's possible that I may be mixing events from different structures that sort of shouldn't actually be composited together, and just sort of ended up with something that looks like a strike slip mechanism. But it, for a kind of a spurious artifact, that mechanism, that's a strike slip mechanism that aligns with the Hosgri fault and the other major structures. So it seems unlikely that that's a completely spurious mechanism, but it might be, mixing some small transform fault that happens to have a lot of seismicity with some of the earthquakes on bigger structures that may actually be reverse mechanisms that just have gotten overwhelmed by some other structure. We would have to go into a lot of detail to try to pull out what happened there, but.
Well, I'm dragging up old history. In the early days, there were interpretations that the Hosgri, rather than running onshore to the San Simeon, ran around, and in those arguments, people were arguing it was a reverse fault, but maybe, we need to go back and revisit, is there a strike slip deformation going out around the point?
Yeah, and I think that's something that's going to have to, I think the focal mechanisms are not of good enough quality to be the final word on that. So.
Okay, yeah. Sorry, any other, yes, Wayne?
Your results and what Marcia showed, with possible exception of the area that Bill was talking about, seem to show a very clear spatial partitioning between regions where there's right bilateral strike slip faulting and regions where there's reverse faulting. Are you pretty confident of that kind of spatial separation? And the reason I'm asking this, of course, is that should be one of the targets of our geodesy program.
So I'm confident of that as a broad scale feature, this sort of transition from strike slip through thrust back to strike slip as you move east. I'm confident of that as a very broad scale structure, but because I'm very dependent on these composite mechanisms where I have to take a number of events over, a 5 kilometer by 5 kilometer box or something, it's more difficult to say with any certainty that all of the mechanisms within that box are all of the predominant kind.
And just to follow up, although spatially distinct to first order on a seismicity map, the separation
between regions where there's predominantly strike slip faulting and predominantly reverse faulting is 20, 30 kilometers. Is that about right?
Yeah, well, I think in sort of the region where the San Simeon earthquake occurred, that's probably a 30, 40 kilometer long region that's predominant. I mean, there's some strike slip in there, that the shallow mechanisms are, for the San Simeon aftershocks, are strike slip. But that's this area that's really predominantly thrust, and then it has strike slip on either side. But when you get down to sort of the San Luis Obispo area, it looks like there's strike slip just on the West Huasna Fault, and it looks like there's strike slip sort of moving inland in Point Bouchon, and there's only this sort of single box of thrust mechanisms that are along the Los Osos Fault. So it looks like kind of the width of this thrust zone between the strike slip looks like it kind of varies from north to south. And
as I'll emphasize in my presentation of the geodetic data, it's really difficult to see features on scale lengths less than about 20 kilometers, mm-hmm. the thickness of the seismogenic zone with geodetic data. So it's quite challenging to be able to quantify this partitioning that seems very evident from the focal mechanism data, but is much more elusive from the standpoint of surface crustal deformation, and to be able to distinguish the relative importance of thrust versus strike slip.
Okay, any other questions? Steve?
Yeah, it's a somewhat related question. There are quite a few FP-fit focal mechanisms, and Wayne pointed out that to first order, they show very similar patterns to the hash mechanisms. Have you considered what should we do with the FP-fit mechanisms? Should those be discounted as poor data? Are there, what cautionary tales would you assign to using the FP-fit data, and what would you comment on in terms of combining FP-fit and hash data if you wanted to look at a larger database? So
my feeling with FP-fit is that when a mechanism is really well constrained, it's well constrained by FP-fit, and not for this data, but when I was developing the hash methodology, I compared a lot between what I got out of hash and what I got out of FP-fit. And when I got like an A or B quality mechanism out of hash that I thought was a stable, good mechanism, it would almost always be the exact same mechanism as the FP-fit mechanism. The problem was that it didn't go the other way, that a number of mechanisms that look well constrained in FP-fit, with FP-fit, they haven't looked at the robustness of that mechanism with respect to changing the takeoff angles, for instance, because those takeoff angles are dependent on the velocity structure. Those takeoff angles can vary by 25, 30 degrees sometimes, which can totally mess up a mechanism. So because they weren't kind of testing the stability of the mechanism, there's a lot of FP-fit mechanisms that look great and get a high quality assignment, but turn out to be fairly sensitive to maybe one or two observations that if you change the takeoff angle, it could change the mechanism a lot. So I would say that FP-fit mechanisms, if all you have is a catalog of FP-fit mechanisms, they're probably giving a good idea of the general, the general style of faulting and fault orientations. But I wouldn't put too much weight on an individual mechanism here or there, because we don't know how stable those mechanisms are.
In the catalog of hash of the single event hash mechanisms, is that work done? The catalog that you produced
yeah.
Do you have plans of continuing with the single event mechanisms, or is all of your effort going into the
So,
composite?
so there is a kind of a finished catalog of that's also available, publicly available from BSSA as an electronic supplement of my 2010 paper. My feeling with either the individual event focal mechanisms or the composite mechanisms that that's something I want to wait to update until we've gone through the velocity model again, and we think we have a better handle on the velocity model, because the takeoff angles are very sensitive to the velocity model. And I think there's no point in doing kind of another iteration of focal mechanisms now while we have kind of a new velocity model in the works. But I think once we've produced a new velocity model, I think it's going to be worth revisiting the individual event focal mechanisms and see if, especially with some improvement of the offshore part of the 3D velocity model, if we can get more stable single event mechanisms or not.
Can you use the new 3D booming noises offshore to improve your velocity model next year when they do larger charges?
Yeah, we definitely could. Yeah, I think that's an area where we should be in touch with people at PG&E about what sort of active source data is available that we could integrate into the velocity model, because that would be very helpful.
You might be able to pick up some of those booms on your
because that would be the most useful is if those sources are also recorded by the network and not just whatever temporary stations are there.
And the impetus for Marcia to get her new stations in.